just to the sensor.
Mm-hmm.
See you. Yes.
Okay. Yes.
Welcome back, everybody. We have a seminar. It's a pleasure to have here Dmitry Kostunin. Dmitry had his PhD in Karlsruhe, in Germany. Then he did his first postdoc actually in Karlsruhe to move then to DESY Zeuthen as a fellow, and he's actually the principal investigator of Tunka-Grande, and he's going to give us an overview of the astroparticle experiments in the Baikal region, which is in Russia and more precisely towards Siberia, if I'm not mistaken. So we're moving geographically, but not climatically in terms of weather. Thank you very much, Dmitry. Welcome to our school.
Okay, thank you for introduction. So do you hear me well, everybody? Okay, nice. And yeah, so accidentally I'm in São Paulo, and so I will give a kind of overview of the astroparticle experiments, which are kind of happening in the almost opposite the side of the globe. And it's a Baikal region, and yeah, we just discuss this a little bit, and yeah, and I will give an overview of this guys, and this is the deepest lake in the world, and yeah, let's start. Okay, so first I just quickly remind you why we actually focus on multi-messenger astronomy. Yeah, most likely you already heard from the Johannes lectures that we have some interesting process in the so-called astroparticle sources, which can emit cosmic rays, gamma rays, neutrinos, and so on. So I will not focus on this very precisely, but yeah, for us it's very important to try to measure all of these messengers from these astroparticle sources, so including cosmic rays, neutrino, and gamma rays. And yeah, let's go further. So might be you might see this this beautiful picture, might be not, but yeah. So we have different processes connecting our different messengers, and so today morning you also seen how actually cosmic rays can produce gammas and neutrinos and so on. So I will not spend much time on this slide. And yeah, so might be also heard about air showers, and so we can detect air showers with different techniques. So air showers, it's a particle cascade produced in the atmosphere by some primary particles like cosmic rays or gammas or even neutrinos of ultra-high energies, and we can detect it from below, from these particle detectors or some kind of light detectors for Cherenkov light or fluorescence telescope, or even from below with satellites. And there are different experiments like Pierre-Roger, so might be you heard about Pierre-Roger experiments, and also IceCube and so on, which can detect these particles. And today I just will focus on detection technique which deployed in Baikal region and the progress of them. So just small historical introduction how actually it's began in Russia and in the worldwide as well. So after 4 years of the detection of neutrino in 1954, so Moisey Markov, a Soviet scientist, actually suggested to deploy a very large-scale detectors either in a lake or in the sea, and to detect neutrinos. So it was kind of the beginning of the DUMAND project. So DUMAND project is a proposed detector in the Pacific Ocean nearby Hawaii, as far as I remember, and yeah, it was started in 1975, and the proposed detector was very optimistic. So it was initially proposed of more than 1 cubic kilometer, more the size of ice cube, with actually equipped with as well with volume acoustic detectors of 100 cubic kilometers, and it was an active collaboration between Soviet Union and the USA until 1980. And actually this project, it was unsuccessful, but it's actually then split it into Amanda and T200, and Amanda then became an ice cube. And today I'll speak about the parallel experiment which deployed in the freshwater lake in Baikal. Okay, so and I will speak about Baikal gigavolume detector. So this experiment goes like this. So it's located here. So yeah, it's Siberia, as I said, and so here you can see a piece of Europe, piece of Africa. So you can slightly imagine where it's located. It's in the border of Mongolia. So this Baikal Lake, it's the deepest freshwater lake in the world. And so it contains about 25% of the liquid fresh water. And the maximum depth is about 1.5 kilometers. So it's so since it's have a fresh, transparent water, and during winter time it's actually covered by a very thick piece of ice, about 1.5 meters. So so actually the gradient of temperatures in this region from minus 30 or minus 40 till plus 20, plus 30 degrees. So it's a really kind of yeah. Yeah. So it's not Fahrenheit, but Celsius. So it's a really big gap, and we actually can exploit this for our astroparticle purposes. Yeah. So if you go a bit closer to this, if you look into maps, so we have a shore, and from about 3.5 kilometers from the shore, where the depth is about 1.4 kilometers depth, there's a detector deployed. And so we already heard about ice cube experiment and the advantages and the disadvantages of this experiment. Today I want to speak about Baikal experiment. So actually we have a railroad there, very old one, and it's like about 100-kilometer via railroad from the nearest big city from Irkutsk. But as well, you can just during winter time you can simply go with the ice, and you actually can reach it very fast, just riding on the ice. Yeah, and so the transparency of water is about 22 meters, and light scatters each about from 30 to 50 meters. And so since we have a fresh water, it's a very nice advantages, and by this we can actually deploy large-scale detectors with a very simple, let's say, instruments. So as I said, I will show you a video a bit later how actually deployment happens. But since we have very low temperatures during winter time, so the lake is covered by very robust ice, and so the construction can be done just putting all of our construction size of ice and deploying optical modules just under the water during 2 or 3 months, winter months. And so contrary to Mediterranean, so we have no background from the decays of calcium salts. So it's really low background. So it's no bioluminescence, no calcium decays, and so only one type of background is kind of chemiluminescence. So it's like some chemical reactions happens and can produce some gammas. Yeah? No. It's due to some chemical reaction. So it's like a low level. It's,
the lake is dead.
huh?
The lake is dead.
No, it's not dead. It's
alive.
it's alive, but since it's cold, fresh water, so bioluminescence, as far as I know, very suppressed, or even no bioluminescence in sense to, let's say, to kind of distort these measurements. And yeah, so it's a kind of complementary location to the ice cube. So since ice cube is deployed in the South Pole, so the latitude of Baikal is 50 degrees, northern hemisphere, and as I say, good infrastructure. So we have railroad, power line, everything. And yeah, this I already said, and I will show a beautiful movie how we deploy this experiment. Okay, and so actually, as I said, after the termination of DUMAND experiments, it was 2 parallel experiments like AMANDA and NT-200. So it's like neutrino telescope 200 with this 200 optical modules. And this NT-200 actually was the first neutrino telescope which detects neutrino in the natural media in 1996. So this kind of actually event detected with only 96 optical modules at that time. It's a kind of full layout. You have just a few strings and a kind of very small detector. In this sense, yeah, it's so since the detector was pretty small, yeah, so it was only put some limits on astrophysical neutrinos, on particles beyond standard model, and detect atmospheric neutrinos, which is kind of very important for estimation of background. There's some historical pictures. So it's a first expedition in 1981. So you can see how people deploying instruments on the lake. So it's like the first optical models has such kind of size. It's actually, in previous picture, in the next picture, so this guy is actually dean of Irkutsk faculty, working on ice when he was a bit younger than now. And yeah, it's the first big tube deployed in 1987 already. And yeah, so after this experiment was a bit kind of suspended because of the decay of Soviet Union and some disorder in Russia and so on. And now since, let's say, 5 years, it's very actively developing. And here you can see the optical model. So it's not very different from DUMAND ones, from Amanda ones, from IceCube ones. As I said, that so everything actually grew up from a DUMAND experiment. Yeah, and the main property is that we have a huge photomultiplier tube looking downwards, and some electronics, and as well it has to be really well isolated because of the pressure of water. But yeah, in principle, the constructor is very the same as present IceCube models, except that so it's not a digital one, but analog one. So actually, signals are sent via signal cables to some local clusters and digitalized actually there. And as well, calibration and so on also deployed with these models. Yeah. Okay. What's the present status of this project? So here you can see few clusters. Sorry. So it's comparing to Russian television station Stankino. So might be you didn't hear about this, but okay. So the length of them about 0.5 kilometers, and so it's 36 modules per string with a 15-meter spacing, so it's very similar to IceCube, deployed on such depths, and 60 meters between strings, and each cluster is actually equipped with 8 strings. And yeah, so we use a laser for the calibration as well as LEDs deployed at some of optical models. And so, as I said, so deployment actually happened. It's happening now, and the first cluster was deployed just 3 years ago, and now we have 5 clusters which are put in operation since this year. So on this one is actually timeline of Baikal telescope. So, and you can see that it's planned to have 9 clusters with about 2.5 optical modules in 3 years, and it will be the area of 0.4 cubic kilometers with full detectors having 1.5 cubic kilometers. But for this, so timeline is not very well defined. So it's like will be 4 different phases of deployment. So the first phase is defined, and we plan to deploy 2 clusters each year. And yeah, then will be second phase, third phase, and fourth phase. Yeah. So this how we deploy. I guess I will show this. Maybe I will show this now. Yeah. So so let me check. This is no, it's not. We'll see. Yeah. So here you actually see the movie from drone, how it's actually happening. So yeah, so you can see that you can simply put very heavy technique. So so there's a kind of 1.5 meters of ice, and then 1.5 kilometers of the fresh water. And yeah, this kind of.
You anchor it down?
Yeah, of course. Just to fix them.
You do it in winter because you can walk on the ice and go to the
Yeah. So here you can see that some special hole is drilled, and the people just inserting or extracting optical modules from this.
Have you ever been swimming in it in winter?
Yeah, it's 4 degrees, so the temperature is very constant. Yeah, you can swim. And actually, so the ultraviolet is very strong there. So I mean, after this, you can have like a very nice dark skin and so on. Yeah. So and it's also one. Yeah. Okay. So yeah. So here you actually can see the sounder picture. So if you kind of scan the water, you can see it's a kind of shore, which also, let's say, introduce some systematics or reflection stuff. So it has to be taken into account very, very carefully. And one of the advantages that you can actually refit your models. So it's not like fix it like an ice cube, but you can extract them and you can, let's say, tune your detector for different energies and so on. It's not like kind of forever. Okay. Yeah. So this is kind of performance. So it's effective volume in cubic kilometers for a different number, for the number of heat of photomultipliers more than 10. And yeah, you can see that for phase 4, the effective volume will be for highest energies up to 2 cubic kilometers. Yeah. And yeah, so this one for muons, effective area for muons, and this is actually angular resolution for muons. So contrary to ice, we expect that resolution will be a factor of 2 better for fresh water, because you can, I mean, first of all, it's kind of isotropic, and then you can really precisely calibrate. So in principle, we can send even Aqual and GIS there to maintain or to install some additional stuff. So working with water much more easily than with ice. Okay, yeah, it's kind of quick slide about data processing. So data processing, actually, the software is based on a Magic software, Magic framework. So it's very nice, and it's written with root, and it's just tuned for a neutrino telescope, and to reconstruct the tracks and making some background signal separation. It's used boosted decision trees and so on. But for now, the software is very actively developing, because I mean, detector is under construction, and very much manpower is spent on actually more instrumental stuff than on data analysis. So only like very simple data analysis is performed. And yeah, here you can see the very first analysis of one cluster deployed. It's like, for example, downward going muon event. So we can see this the same legend as an ice cube. So the size of this bubble is actually denotes the amplitude, and the color denotes the charge. And yeah, so here you can see actually the so since the threshold is set to a very low value, so we have a lot of noise, and by some different bootstrap method, the noise is reduced, and here you can see the actual reconstructed trace for neutrino event. And so it's a background muon bundle from cosmic rays, and here's a cascade. And yeah, so the first scientific results from the detector is follow up the gravitational waves. Wave detected in 2 years, yeah, almost 2 years ago. Yeah, and so here we can see the limits put by Baikal. So it's even at some point even a bit better than Antares, but it's done only with a very small part of detector. So and yeah, so that's my summary. So so the first cluster is about 300 optical models. It's operating since 3 years. And for now, we have 5 clusters. And so now the detector is deployed about 2 clusters per year. And yeah, so we're expecting some very interesting physics results. So if you have any questions, so let's ask now. And I will move to another facility located in Baikal region. Okay, so if not, yeah. This is data. Yeah. Sorry? It's also very bad as for ice cube, so it's just several degrees, roughly speaking. Okay. Of course, depends on the cascade geometry and so on. But for muon, we expect like 0.25. Okay, so any other questions? Okay, so let's move further. So it's the next experiment located more or less the same regions, Tunka Advanced Instrument for Cosmic Rays and Gamma Astronomy. Yeah, so it's located. So since Baikal experiment was here, so if you go a bit about 50 kilometers from the southern tip, we will see such kind of array. So it's a map of it. It's many different detectors. So I will go through them and describe in detail. So actually, initially it was Tunka-133 cosmic ray experiment for the cosmic rays in PV to EV region, and now the facilities consist of 3 cosmic rays detectors, which detects cosmic rays with energies below exelectron volts, and as well 2 gamma ray detectors, one wide field Cherenkov detector and the telescope. So here you can see, okay, so green circles, red crosses, and black squares is a cosmic rays detectors with such kind of cluster structure. You can see it here. And so HRSCORE, it's a kind of regular grid of wide angle Cherenkov detectors. And as well, you can see 3 telescopes. So 1 is already deployed and two in construction. And yeah, this one is a kind of engineering facility. I just will say a few words about this later. Yeah, and actually, so again, some small historical overview. So actually, cosmic ray experiment started from the ice of Lake Baikal because this, let's say, it was kind of one of the pioneering wide-angle Cherenkov detectors, and they were just installed on the lake of Baikal and triggered by the small neutrino telescopes, and seeing some coincidence with the cosmic rays detected by neutrino telescope and by Cherenkov detectors. And yeah, then they moved to Tunka Valley already, and yeah, actually with a big support of Michael Hillis and Gianni Navarra, so we obtained PMTs and some instruments from Italy, from Quest experiment. And sorry. So Quest was used for calibration, and the former Marco experiment actually gifted us some photomultipliers for the first prototypes. And so, and the experiment was actually commissioned in 2009. So for now, it's like 10 years of kind of large-scale cosmic rays in Tunka. Yeah, so it was like Tunka 13, then Tunka 25, like here, and then Tunka 133, in the final stage of Tunka Cherenkov telescope. So it's a timeline, and actually after commission of Tunka 133, it was a Tunka Rex radio detector, Tunka HRSCORE low threshold gamma ray detector. Tunka-Grande is actually from built from a former Grande extension of Cascade experiments with the same, more or less same layout. And yeah, the first Cherenkov telescope was commissioned in 2016, and yeah, now we're doing open data of some of the old experiments and so on. Yeah, so here is a kind of look like, again, you can see winter, yeah, with a lot of snow. So this is how cosmic ray experiments looks like. So it's a radio antenna. It's an optical detector of Tunka 163. This is housing for a Tunka-Grande detector. And this is kind of a single cluster of these experiments. And yeah, what is the science objective? So as for typical for cosmic ray experiments, yeah, we have to measure with a high precision energy spectrum and a mass composition. And so in our layout, we have a kind of object of interest is a transmission from galactic accelerators to extragalactic accelerators. So it's about 10 to 17, 10 to 18 electron volts. Yeah, and so we're doing, as I said, just all particle spectrum, actually covering first and second NIS, and the mass composition, and so have a lot of instrumentation studies, which some of them already widely used by another experiment. So so it's non-imaging error Cherenkov techniques. So just a wide field wide field of view ground detectors and so particle detectors. So we're trying to combine colorimetric measurements of radio and air Cherenkov with the particle measurements for the mass composition study. As well, we are one of the kind of first next generation of radio techniques, so Tunka-Grande experiments, which I'm working with this, and I just will maybe show a few slides after this. Yeah. Okay. So how the single cluster of Tunka facility looks like? So now it's like a more panoramic picture. So we have a cluster center here with electronics, optical model. So one can see here, there. So it's like a flower, yeah, like a hexagon. And actually 3 antennas, 2 of them connected to Tunka-Grande. And yeah, this is actually underground detectors. Here's on ground. And so yeah, here's actually written that we have 7 opticals modules, so 6 in a hexagonal structure, 1 in the cluster center. And we have on-ground and underground scintillators and 3 antenna stations operating in megahertz range. So it has about 19 dense clusters within area of 1 square kilometer plus 6 satellite clusters expanding the area to 3 square kilometers. Okay, so it's let's say photo of a single optical model of Tunka-133. Yeah, so for now we have, as I say, 25 clusters times 7. Yeah, it's actually has an independent trigger for each cluster. So when we have air shower which highlights more than 3 optical models, so the data is digitalized and sent via optical fibers to the central DAC, which gives us a timing resolution of better than 5 nanoseconds. And yeah, since it's optical detector, so it's measurement during moonless winter night. So it's the size of PMT like that one. It's very huge. It's comparable to one used for neutrino detectors. So Tunka-Grande, so as I said, it's kind of on-ground detectors, underground detectors, very similar to Cascade-Grande, and it has a almost full duty cycle and energy threshold of about 10 to 16 electron volts. And yeah, so here's a kind of detailed layout of this. And yeah, so radio extension, so it, just radio antennas, which measures coherent radio emission from the air showers, as we discussed today. So there's ANITA experiment, which is using, roughly speaking, more or less the same technique, but ANITA is a kind of balloon experiment with many antennas concentrated in a single place, while Tunka-Rex is just a sparse detector on 3 square kilometers equipped with such kind of antennas. So it has a kind of amplifier in antenna, and then data sent to the cluster center, and this kind of analog filter and so on. So radio technique is kind of complicated because we have a lot of RFIs and background and so on, but with let's say modern ideas, electronics and computing techniques, we actually can extract very useful information from radio as well. But it has a pretty high threshold. Yeah, and what is nice that we have an absolute calibration of the radio detector, and we can reconstruct an energy with the radio with a resolution comparable to actually to optical detectors. So we can really get on colorimetric information from the air shower with a resolution comparing to fluorescent or Cherenkov, but with a full duty cycle. So we kind of can gain a factor of 10 in our exposure. And yeah, so here, now I will show you some example events. So as I said, we have a ground detector, and we see actually footprint of air shower, as actually shown by, similar shown by Johannes today. So when we put a detector on the ground, so we can see kind of footprint. And yeah, here you can see that the size of the circle is proportional to the amplitude. Yeah, we can see that actually shower like coming from this direction. Yeah, there is no signal, and the shower core is around here, and we can produce also a lateral distribution function. So it's a function. It's a amplitude as a function of the distance to the shower core, and we can also produce a timing and reconstruct a shape of the front, how it actually arrives. And this is actually simple PMT signals detected by a single optical model. It's an example of event of Tunka-Grande, so you can see more or less the same. Some shower coming from this direction, highlight some antennas. We can also produce very similar lateral distribution function, but actually signals look like this. This is a very good example. So this SNR about 100, so it's very rare event. So usually we have SNR of 10 or something like this. And since both Cherenkov and radio emission are produced by the, roughly speaking, same particles and also beamed, so we actually have a very similar distribution of amplitudes. Yeah, and the Tunka-Grande, so it's just a particle detector, so you can also see here very common picture and the lateral distribution function of these events. Yeah, so the concepts of air shower reconstruction is so pretty simple. So either we can use some more sophisticated techniques like template fitting or neural networks or whatever used by, for example, Hawk. But the main idea for cosmic rays is that we have this lateral distribution function, and actually slope of this function is proportional to the distance to our shower maximum, which actually corresponds to the primary particle, and amplitude at some reference distance corresponds to just colorimetric amplitude of the cascade, or we can just integrate under this curve. So, and yeah, this example for radio, but for Cherenkov it's almost the same, and actually the model parameters can simply extract from Corsica simulation and so on. So, so I really like this electromagnetic part of air shower because we can simply obtain a very nice reconstruction of main properties of the cascade, contrary to measuring of particles, especially muons, because with muons we have many problems in our models actually. Yeah, and so precision of air shower reconstruction is given here. So yeah, since for this energy of cosmic rays, so angular resolution is not important for us, so we just stay at about 1 degree. The core position is about 5 meters, energy from 10 to 15, shower maximum from 20 to 40 grams per centimeter square. So it's kind of very nice and similar to what Auger gives to us. And yeah, if we combine particle detectors and the radio detectors, so it's a bit lower, but it's like in progress. Oh, sorry. And we are working on this. Yeah, and so techniques for, so as I said, we developed many techniques, for example, for sparse radio arrays. So if you can see the lateral distribution function for LOFAR detector and for Tunka-Grande, so it's, you can see that the number of input parameters differs by about 100, factor of 100. And by this, it's actually very relevant for the next generation of detectors, because the next generation is kind of putting all antennas like in every, like from 1 to a few kilometers, and by this we have to actually somehow manage this and somehow obtain a very high resolution. And for Tunka, we actually testing this stuff, and yeah, we see that in principle we can use some simple parameterization and so on, and receive a results comparing to very dense detectors. And as well, we can use some more sophisticated technique, like using a template fit from the simulation, and we can even reach a resolution close to optical detectors. Okay, so let's come to some physical results by Tunka facilities. So we can see the all particle energy spectrum reconstructed by Tunka-133. Yeah, we can see knee-like features and so on, and actually we compare it also via radio extension the energy scales of Tunka-133 and Kostunin, and actually, yeah, we kind of see these features are in the, let's say, in a very agreement in the energy range. So as well as the structure, but these scales is also are in agreement with the Kostunin experiment. So if you go to higher energies, we can also reconstruct some spectrum with radio. So this large error bars, because we have much smaller statistics for radio detectors. And yeah, so as I said, we also did some cross-check in energy scale and shower maximum scale between Tunka-133 and Tunka-Grande, and we can see that they're in a very good agreement, so like a one-to-one agreement. So we can say that, yeah, we are really clearly understand the different emission from the electromagnetic component for the moment. And yeah, as I said, we cross-checked Lopez plus Cascade-Grande and Tunka-Rex plus Tunka-163. And yeah, we can see that the energy scales are in agreement within some systematic uncertainties. And actually, these features have the same energy scale for both experiments. Yeah, and as well, it's actually old plot with shower maximum. So the new plot shown by in present ICRC are really now really pessimistic when LOFAR puts some points here. Yeah, and there's also some people who was in ICRC saw some disagreement between Tunka and telescope array. Yeah, so but yeah, at least we can reconstruct something, and now community have now has to somehow actually clean it up and finally see what's the problem with the disagreement. But this previous plot are very nice. And, yeah, sorry, I forgot to put a new one, but new one is much worse for now. Yeah, and yeah, so you can simply actually convert shower maximum, statistically shower maximum to the mass of the primary particle, and yeah, this is also this point just results from Tunka-163 and can be also compared to Auger results and so on. And there was some attempts to make a light-heavy mass separation like in Cascade-Grande, but this is actually very old results and unfortunately have not been updated for the long time, so it has to be updated with the larger statistics. And yeah, the same, but for 4 groups, yeah, you can see that the uncertainties is really huge. Yeah, and as I said, so yeah, to reconstruct the primary particle 1 either can use shower maximum like here, but here we can see that actually kind of merit factor between iron and proton is not really nice. But if we know the energy from some, let's say, third-party source, like for example from Cherenkov or from radio, and using number of muons, we can really distinguish of these 2 components. And yeah, by this now we are trying to combine radio measurements and particle measurements, and as well the same work is going in Pierre Auger Observatory. 10 minutes, okay. Yeah, and so some limits on diffuse gamma flux, very preliminary. And so let me come to gamma ray instruments. So the first one's a Hegel-like Cherenkov telescope and a wide field gamma telescope called HRSCORE. It's an imaging Cherenkov telescope. And the concept is that we can measure both footprint and reconstruct direction energy from the footprint, and even we can make a kind of muon vector with the muon detectors, and we can very sparsely put Cherenkov telescope which operate in a monoscopic mode. So actually we take all shower information from the on-ground detectors, and then we just see in the image as Johan has shown on the morning, and by shape of this image we can say, okay, was it gamma or a proton? So by this we can really increase the effective area of detectors by placing Cherenkov telescope on every 600 meters, for example. Yeah, so an objective is very standard for a gamma ray telescope. I will not focus on this because I have a lack of time. So the sensitivity is kind of extending Hawk to very high energies. And so the HRSCORE detector is like a kind of inclined wide angle telescope. And so this inclination is actually motivated by the increase in the exposure. So the first prototype was kind of fixed and pointing towards scrap. Now there is some kind of mechanical construction. So in principle, since this telescope is fixed, it moving a little bit. Yeah, and here you can see the row of this telescope. So it's like a really regular structure of them. And yeah, so the signal very similar as for Tunka-163. So its principle, it was the experience acquired in Tunka-163 was kind of digested, and the new detector with a threshold lower and several times was built, but using the same technique, but with more sophisticated light acquisition. Yeah, so the example of events, yeah, very similar. Yeah, and here, So since every gamma detector can also detect cosmic rays, so we can produce cosmic ray spectra covering the far orders of magnitude. So in principle, Tunka facility connects satellite experiments with the Pierre. So it's really like covering the huge range. And in principle, yeah, we can see that there is nothing, I would say, it's nothing surprising or special in energy range spectrum if we properly analyze the data and so on. Yeah, the funny thing that we detected a LiDAR from International Space Station. So we found some kind of very strange events with a very plain wavefront moving with a velocity of 7 kilometers per second, just covering the covering the detector with a very strange behavior. And then, yeah, okay, so it was not astrophysical region for sure. It was very kind of sources with infinite distance. I mean, roughly speaking, infinite. And yeah, so we actually then discovered it was just ESS. And by this, actually, ground detectors can be calibrated with a very high precision. I mean, this kind of independent source of the. Huh? Yeah, it's actually have events covering the about 100 square meters. It's a LiDAR from the ESS. LiDAR, laser.
Oh, the laser. Oh, okay. Is it pointing a laser down?
Yeah, it's kind of for some studying for atmosphere or something like this.
Okay, so there is an active source on the
Yeah.
pointing the
Yeah, and since as I shown, so the front of air shower have kind of curved structure, but this front was completely plain and moving very fast. So it was like a so it was like several events, and the distance between the cores was like it moving with 7 kilometers per second. Yeah, this is orbital velocity, and yeah. Yeah, and so it's properties of telescope. As I said, it's like a Hegel-like telescope, which described by Johannes Monin, and so it's production DUMAND and mirrors. And yeah, so here you can see like the first prototype camera installed. So camera consists of about only 500 pixels, but it's optimized for the very high energy events, starting from 10 TeV. So Johannes today saying about 0.1 TeV, so we're just in 2 orders of magnitude higher, and we focused on these energies. And there's also TAIGA-muon concept, so it's just simple underground muon detectors to just make increase the confidence of the gamma events reconstruction. So it's very kind of simple particle detectors with a single solid state PMTs. No, it's not solid state. Sorry, it's classical PMTs. Yeah, and so joint operation already taken, and so the collaboration decided to publish first data when it will analyze the first 50 hours of exposure with CRAP and Markarian 421. Yeah, so open data outreach and blah blah blah. So we have joint project with Karlsruhe. So yeah, so since I'm working in Russia and Karlsruhe and so on, so we kind of starting to do some open data stuff based on actually on KCDC concept. Maybe you heard about open publicity of Tunka-Grande data, and I guess I will skip these slides. You can see it maybe later. Yeah, and so what is also very interesting stuff that, yeah, as I said, we go and mesh Tunka-Grande data, since both experiments actually located in the same latitude and has an overlap in exposure and so on. So it's like a good opportunity to try to combine different techniques, different data, and see what can come out from here. And maybe we can put more stricter limits on chargers, so-called chargers, messengers. And so it turned out that these loop antennas were a really successful instrument, and we deployed them in Tianshan in Kazakhstan, in Argentina, and for now the large-scale radio array is funded. So the Pierre Observatory will be covered with, I mean, each tank, I think this one is confirmed. So each tank will be equipped with this loop antennas, and now they're modifying this technique, and as well in Spain. So So radio now it's kind of going to be really large scale, and it's already approved. So in few years, Pierre will be equipped with radio. It's fund given by to Jörg Horrendel, just for your information. Yeah, and we also deployed some educational cluster, and it turned out that we are going to do some cosmology, not with this cluster, but let's say study some systematic for this very famous 21 centimeter cosmology. We can discuss it maybe on coffee break later. Yeah, and so just last 2 slides, I want to show that we, in Tunka, just very close to our optical detectors, we have also one of the telescope from Master network. And for now, so Master is like also one of the first optical instruments there. It's working not for cascades, but just for optics. And it's actually a fast-moving telescope and following all transients. And yeah, so Master is kind of a network of telescope. So most of them installed in Russia, but there's one in Argentina and one in South Africa and Southern Hemisphere. And actually from the scientific output, Master is now it's a most successful facility. So it's not really a high energy astroparticle, but I should mention it as well here. Yeah, and so we can say that yeah, we have a really kind of multi-messenger activity in our region. And so I'm happy that I kind of informed you about what's happening there. Okay, thank you very much.
Questions? I asked a lot of questions. Come on.
So Dmitry, I have a couple questions, if that's okay. One of them is to do with the DAC system that you're using on TAIGA. So have you got a multi-channel DAC that's going on? Are you doing like similar to ICU, ATWD, FADC, or are you using like some new technologies or?
You mean for neutrino telescope or for TAIGA?
For TAIGA.
For TAIGA, so for now we are using just improved, I mean for gamma. I mean for cosmic rays, DAC is very simple. It's like just traces digitalized with 200 megasamples per second, and we have a resolution of 5 nanoseconds, which gives us angular resolution of 1 degree. But for gamma telescopes, the system was improved to achieve the 1 nanosecond resolution and 0.1 degrees. And as well, there is a parallel test bed for a white rabbit. So, I mean, since we have a really small experiment, we can just connect everything with the optical fibers in TAIGA. Okay. So it's only like 1 square kilometer. It's like I don't know, awesome. few tens kilometers of optical fibers, or about 100. It's not too much. So it's, I mean, we can do it as best as we can. So contrary to Pierre, which they have to transmit data with the wireless, yeah, we can connect everything with the fibers.
Okay. My second question was to do with the neutrino telescope. So what's your largest systematic uncertainty? I worry that if you have this freezing and thawing of the lake, you may have, for example, I don't know, bubbles or something that you have to keep testing and calibrating.
Again, for what experiment?
For the neutrinos.
No, for neutrino, so actually the systematic uncertainty due to temperatures is very low because mostly temperature in the Lake Baikal it's about 4 degrees, even during winter time. So, and as well, it's very well monitored. So the systematic can be controlled, but there is no really huge fluctuation in the temperature of water.
That's not actually my biggest worry. So the temperature, of course, you can control. But for example, if you have to reconstruct events inside the detector, if you have bubbles and so on.
Bubbles?
Yeah,
you mean bubbles of air?
You drill in ice, right? So you go between the two, right?
If I understand, maybe I'm mistaken, but your detector is water. It's just covered in ice, right? And your data taking is all over, or you consider events all over the season?
So in the very depth layers of lake, the temperature is constant and it's about 4 degrees.
30, okay.
It's like 4 degrees. So it's actually a problem for acoustic detector because it's a maximum density of water, and so acoustic waves cannot really propagate. So we tried to also play it with acoustics, but it turned out that the threshold is very high.
Okay, yes, that's fine.
More questions for Dmitry? I guess we're all exhausted. So we can thank Dmitry again. Thank you very much. And I'm sure that if you have questions, you can ask him tonight at dinner. No, I don't think so. But so I'll see you tonight at... you have a question, Carlos? Okay. You could have told me when I was up here.
I have like two questions. One is just for you to speculate, and the other one is an actual question. You said that you can move the detectors, like, and you can redeploy them, right? So
Yeah.
you can move them around. So I guess currently the separation of the detectors have been optimized for some energy. So how do you optimize your current separation? So that's one point. And the second one is you show the results of the X-max measurements, and they are very different from the year messengers. Can you comment on that?
Okay, so I guess Xmax will come first, yeah. And you mean this plot, or?
Yeah.
And what's your question?
I mean, what's your definition of what the numbers? Can you comment on what you think, what's causing the difference between your messengers and the year?
So let's say if you look in the very last results, in the ICRC, so Xmax point of flow are really low. And I actually do not believe them, but I have no idea why it happened, because actually for radio, we are kind of, our points is moving towards Auger, so it's moving, let's say, lighter composition.
I mean, the radio ones look like, somewhere in between jumping, but the blue ones
but
systematically low.
You mean Tunka-Grande?
Yeah, that's right.
Yeah. It's actually a big question, because we working together, but we have completely different reconstruction. And so these points are not correlated, and moreover, as we can see from low energy extension, so Tunka goes in such direction, and tail goes in a heavier direction. So it's completely different behavior at the lowest energy. So might be it's a kind of systematics of Tunka-133. So yeah, I completely agree that we are in disagreement with Tunka-133, but our reconstructions are completely different. So there is some.
It's the whole energy range, right? All of it.
Sorry?
One thing that I'm concerned about is your error bars the 133, they seem to be smaller toward lower energies. And
Yeah. I mean, this is a number of events reconstructed so far, so you can see that these points are not so kind of statistically confident. Yeah, but yeah, what I can see with a more sophisticated, it's written in our paper as well, in this one. With a more sophisticated analysis, we start to see some really kind of shift against Tunka-133. And yeah, so it's some kind of evidence that Tunka-133 has some systematic which are not taken into account, or maybe there is some problem with reconstruction.
Because the shift is clearly parallel. I mean, it's between Auger and 133.
Yeah. And the last results of LOF are even lower than Tunka-133. So now it's completely mess, I would say. And I think maybe we try to spend these 2 years until next ICRC to figure out actually what the problem is. I mean, I can show you a few plots, and you can see it's a really disaster. So now Xmax is completely in disagreement for all experiments.
So more chaos in the composition problem now. So what about the optimization?
Sorry?
The distance of how do you pick your initial separation?
You mean between detectors?
Around, so you're picking some particular initial distance. Okay. How do you guys optimize it? Not for the neutrino detector, not for the...
For neutrino, how we... the second question. So I'm not really sure how this is done, because it's done by Baikal collaboration, so I'm not kind of a member of Baikal collaboration. But yeah, it was done to tune for astrophysical energies. So in principle, there is some ideas to make them really dense, to measure oscillation like in a dense detector of ice cube, or which gonna be deployed, or Orca, I think, Orca.
I think Orca is in the Mediterranean.
Yeah, in Mediterranean. So yeah, there is some ideas, but now, I guess it's just based on simulation to tune for energies of 100 TeVs to PeVs, take into account the attenuation length of water.
All right. Thank you very much again, Dmitry. So the way it's going to work tonight is that we will be there at 7:30. There are some tables reserved for us. we're gonna sit down and get the food. But the keyword, if you don't want to pay for the food, is UNESPI. Okay? They know us as UNESPI, not ICTP-SAIFR, which is written here. Okay? Yeah. UNESPI. And in any case, make reference to me. I'll be there from 7:30 on. Okay? See you tonight.